Good morning, ma'am, class, everyone today present. Today I will be presenting on Niels Bohr and his atomic model. My name is CADET Juan Herrera Vasquez, and I'm delighted to walk you through the key contributions of Niels Bohr to modern physics, with a special focus on quantum physics and the atomic model. All right, and how you guys can see in this slide, the purpose of this pre is to provide a concise history of Niels Bohr and highlight his groundbreaking contributions to atomic theory, and discuss how his work laid the foundation for quantum physics. Here's the agenda for today, as you guys can see it. And we will start with the historical setting, and then we'll explore who Niels Bohr was, and we're going to delve into his contributions and conclude with discussions and references. All right, class, I just want to start this part of the slide. In 1913, for our course test, we had the Bohr model of the hydrogen atom and the quantized states. We're going to be seeing this equation in some of the other samples, as well as the Rydberg constant. And you all can find these equations in the PRC, specifically this one, with the difference that is going to add the C number, the atomic number of the element. And then we're going to be using the Planck's radiations law with Planck's constant, which is in the RDC as well. And we had the phenomena of the waves and particle and how they behave, and this equation is as well on the PRC. And to start with some historical setting of the time that Bohr worked on his atomic model, we had events that happened in 1913, which was a crazy time to be alive. It was pretty much a year before the World War One, so we had that in January. Joseph Stanley traveled to Vienna, and there were some characters in this time, like as Hitler and Trotsky and Tito, who will be the bad guys in World War Two. And we also had in March, Woodrow Wilson is sworn as the 28th president of the United States. And in May, Igor Sarkovsky becomes the first person to pilot a four-engine fixed-wing aircraft. In July, Romania declares war on Bulgaria, and October, Ford becomes the first automobile production facility to implement the moving and assembly line. And we know that it was due to the automobile that they were developing that it will mass produce in the United States. And in December, the US Federal Reserve System was created. All right, class. In this slide, we're going to talk about the person who made everything possible, and that was Niels Bohr. So let's start with Niels Bohr. Was born on October 7, 1885. He was a Danish physicist whose work forever changed our understanding of the atom. Bohr was a middle child in an academic family, with his father being a professor at the University of Copenhagen. His life was one of service, not just to science but also humanity, as he helped many Jewish scientists escape Nazi persecution. He even made major contributions to the Manhattan Project, creating the igniter that would ignite the plutonium weapon. As you guys can see in our slide, we have a picture of Bohr and Einstein sharing a long conversation, which will be typical for their development of relationship that they had throughout the years. They would mostly talk about the uncertainty principle that Einstein didn't accept into the quantum physics world, and other issues about like the war or the typical philosophy theme that they had between each other. And we also have a picture here below of the Solvay conference in 1927, where major scientists of the world contributed and talk about many issues that physics was facing at that time. All right, class, before we continue with our presentation and our main topic, I want to take a moment to appreciate what I often call the Avengers Assemble of the scientific world. The Solvay Conference of 1927. Imagine some of the greatest minds of physics coming together, much like the Avengers uniting to face a universe-shaking challenge. The Solvay Conference wasn't about saving the world from aliens or robots. It was about unraveling the mysteries of quantum mechanics and redefining our understanding of the universe. This gathering featured intellectual superheroes like Albert Einstein, Niels Bohr, Marie Curie, Werner Heisenberg, and Erwin Schrödinger and more. Each of these giants brought unique superpowers to the table. Bohr's quantum theory, Einstein's relativity, Heisenberg's uncertainty principle, and Schrödinger's wave mechanics. Together, they engaged in debates that still echo in physics today. A famous moment from this conference was the debate between Bohr and Einstein, with Einstein being skeptical of quantum mechanics, famously saying that God does not play the dice. Bohr quickly on his feet, countered by saying Einstein stopped telling God what to do. These debates highlighted the passionate quest for truth and understanding that redefined this assembly. This was more than a meeting, it was a clash of ideas that helped shape modern physics. And just like the Avengers, their combined efforts accomplished something no one could achieve alone, the foundation of quantum mechanics as we know it today. So when we think about the Solvay conference, let's remember it is a team of scientific legends whose contributions continue to inspire and guide us, much like how the Avengers protected the universe. Before born, the atomic model went through several interactions. The plausibility model by J.J. Thomson and Rutherford's planetary model were key for our understanding of the atom. However, Rutherford's model had flaws. It couldn't reconcile with classical theories with observed atomic behavior. This is where Bohr stepped in, combining quantum principles with an atomic theory. And as you guys can see here in our slide, we have an example of the famously known as the Plum-Pudding model, which was developed by Thomson, which described the atom as basically a ball of positive charge energy with invasions of electrons among this Plum-Pudding model. And then we had the Rutherford atomic model that finally redefined what the atom was, and that the atom possesses a nucleus with the protons and neutrons in the inside and the electrons orbiting around the nucleus. Let's talk about one of the most famous experiments in physics, Rutherford's scattering experiment, often referred to as the Goldfold experiment. In 1909, Ernest Rutherford and his team, including Hans Jaeger and Ernest Marsden, set up to investigate the structure of the atom. They fired positively charged alpha particles at a very thin sheet of gold foil, expecting most of them to pass straight through it. After all, according to the prevailing Plum-Pudding model, the atom was thought to be a diffuse cloud of positive charge with electrons embedded in it. There was nothing dense enough to block or deflect the particles. But here's the twist. While most particles did pass through, some were deflected at large angles and a few even bouncing straight back. This was completely unexpected, as Rutherford famously compared it to firing a cannonball at a tissue paper and having it bounce back. The experiment revealed something groundbreaking. The atom is mostly empty space, with a dense positively charged center. The nucleus at its core. This overturned the Plum-Pudding model and laid the foundation for the nuclear model of the atom. Rutherford's experiment wasn't just a milestone in atomic physics, it was a turning point in how we perceive matter itself, showing us that the tiniest building blocks of nature hold mysteries far beyond what we could imagine at that time. And all of that finally moves to the Bohr model of the hydrogen atom, where Bohr proposed that electrons occupy specific stationary states or energy levels around the nucleus and transitions between the states involving the absorption of emission of energy in the form of photons. His model not only quantified the size of the hydrogen atom, but also introduced the idea of quantized energy levels as a concept of crucial quantum mechanics. So basically what we're talking about here is that his model was born from the idea of the hydrogen atom, because there was a big problem with Rutherford's model that basically consisted of the attraction of the electron into the nucleus, since opposite charges attract to each other. With Rutherford's planetary model and the classical mechanics physics equations that he used, describing that the electron will eventually come back to the nucleus, and as we know today, that does not happen. So that's when Bohr came in and explained the different energy levels where the electrons stand and stay as an orbit around the nucleus of the atom. So what was that Bohr found about? He found out about the stationary states, where the electrons orbit around the nucleus at a certain levels of energy. And as you guys can see here, his concept of stationary states, divided in different energy states. These energy states would jump from the dynamical equilibrium of the system from the top of the levels down into the first level. And as you guys can see here in the illustration of the transition between the stationary states, we can see the different series developed by scientists who work along Bohr to understand and which and what were these states. We also had the equation of the dynamical equilibrium of the system here, as well as the frequencies and the wavelengths of the absorbed photons. And this specific equation that is in the RDC that accounts for C, which is the atomic number. As you guys can see here, I have an example from the book. This is example 4.8, and it's going to help us understand the equations that I previously demonstrated in the slides before. So to understand what are the different components of the atom, this exercise is asking us to calculate the wavelength from different atoms going from the third orbit state to the second orbit state. As you guys can see, we are given the hydrogen, deuterium, and tritium atom, and we are asked to calculate their different wavelengths. Using the equation 4.30 from the book, we can replace it by using the Rydberg constant and spread in each element. And using their masses, we can find the Rydberg constants right here. So we can find the masses of these elements in the appendix B of the class book, and the electron mass as well. By using their masses, we can find out the different Rydberg constants of the elements, and by using that constant, we can find the wavelength going from the stationary state of the third orbit to the second orbit, and we find out that is almost 13% of the Rydberg constant. And with that itself, we do a movement of the equations here. What we do is that we move the wavelength up to the side, and then we move this part of the equation down here to divide 1 by this fraction over here, and that's how we find the different wavelengths of the elements in nanometers. And to evaluate, we calculate the significant figures, and we understand that significant figures matter in the quantum world. As you guys can see, there's not much difference between wavelengths of these elements. So one specific thing I wanted to highlight in my presentation is the different debates that these scientists had to have in effort to find the real question in hand. What was the atom? And I would like to highlight this specific event where Bohr and Einstein in the Soviet conference had a debate about the uncertainty principle of Heisenberg. This debate explored the nature of quantum mechanics, and it continued to inspire physicists today as we push the boundaries of the quantum theory. After I conclude with this presentation, I will be showing the class the video. Now I'm going to pass to my references. As you guys can see here, these are my references. If you guys go to my presentation posted in the canvas, you guys could directly click into the references, and they will take you exactly to the website where I got the information from. And here are my actual references of the class. And now I will open to the class for questions, and as well as to watch the video that I was going to demonstrate before. All right, I hope that everybody has a great day.